All right, so I hope everyone is coming. So we start in 30 seconds. I see Barry Lou has already a question. And what is it, Barry? Okay, never mind. All right, good time of the day, everyone. This is the series of epic online technology meetings provided to you by the European Photonic Industry Consortium. And today we talk about the integrated photonics manufacturing with our partners from Tosia in Taiwan. Let me remind you quickly that EPIC is the largest photonic industry association in the world. We include over 800 corporate members, and we're there to support you with technology and marketing expertise. So today we have a very exciting agenda of the meeting. We have 3 speakers representing European industry and 3 more representing the Taiwanese manufacturing industry. So we'll hear the talks from Alpha-Lume, APAC Optoelectronics, Focuslight, Wave Splitter Technologies, Tech, and Iratech. I'm glad to welcome all the speakers in the room with us, and also my co-moderator Elaine Chen. So nice to have you. And so this is the first meeting we have and together, and hopefully we will continue in the future in the same way. So without further delay, I'd like to start our meeting with a keynote presentation from a very exciting speaker, Alexei Kosh. He's the CEO of Alpha-Lume, and Alexei will talk about the quantum dot lasers, a step toward easier integration with photonic integrated circuits. Alexei, are you with us?
Yep.
Great. So whenever you're ready.
Yeah, I'm ready.
Please go ahead, share your slides, and the floor is yours.
You have to stop sharing yours.
Okay.
Okay. Thank you. Do you see my screen now?
Yes, very good.
Okay, yeah, but Ivan, thank you very much, and I'm especially excited, to present it for Taiwanese Association, because I spent like several years in ITRI, many years ago in Hsinchu, and I should say Taiwan. It were those who are my favorite years, in my life. I went everywhere, Kentin, Sun Moon Lake, Alisan, all of those places. Okay, so let me go to, let me see where I can. Okay, so the outline, that indeed today, development of cost-effective and reliable photonic integration technology is like really the key to unlock the huge volume potential for photonics. Actually, if you look into all what's happening with AI right now, and I'll show a couple of slides on that there are billions of 200 gigabit per second equivalent optical channels will be needed, per year, and the number will keep growing. And the major key here, in order to really unlock this potential, is to make cost-effective and reliable photonic integration. Then I will briefly touch like technology landscape and competition. How do we see it at Inalum? And say a few words about the company, and then we'll cover the topic why we believe quantum dot technology can really support such an effective integration because of those unique features which we have compared to traditional indium phosphide CWDB technology. This is picture, you know, from actually father of modern data centers, Andy Bechtolsheim, co-founder of Arista. And it's a good point stated here that really like AI changed everything. So the demand, and it's not a bubble, you know, it's not a telecom bubble like 20 years ago, it's real. And the demand of the power of those models is so big that actually what we do, this physical layer, we're not in time, you know, to catch up. Even if we keep growing like crazy, like all those market prediction shows the potential growth, we still, you know, cannot support that growth of what is envisioned for overall models power. It's like, you know, silicon is improving only 2 times for 2 years, and like photonics is still much worse till now. And it's interesting to see, you know, that this is most reputed company in marketing, like counting in the United States, and these guys are changing their forecast every half a year, you know, to higher number of channels, basically to high number of optical transceivers to be built. They keep growing every half a year. They keep growing their predictions, and now it's interesting to see where their own present the comparison of what they predicted in March and what they predict now in October 24. So also what we expect that the transition from 800 gig, let's say DRA transceiver, to 1.6 terabit will happen much faster than any predictions, even from such an optimistic agency as Light Counting. So we expect that really, and also when we calculate these numbers, we calculate not only bottom up, like Light Counting is doing, but also top down when we look into the demand of those switch manufacturers, those guys who build those switches where you have to plug your transceivers. And we expect that really 1.6 terabit will start to dominate the market, you know, by middle of 2026. And that's why all the technologies we're looking at, they have to support such a speed. Interesting slide from Malaga forum on photonics, which took place about 1 month ago. Now it's like picture getting famous because if you look into the left side, in integrated photonics, you have only 20% of value for your photonic chips, and 80% comes from packaging and testing. Whereas for electronics, for silicon, you know, it's vice versa. So the main value is in the chip, and packaging and testing occupies much smaller percentage of that value. And now, you know, recently NVIDIA even bypassed Apple in their market valuation, and this is unbelievable things, you know, company which is making just silicon chips, you know, they are now worth of much more than such a company as Apple. So if you look today into transceiver manufacturers, right, and majority of them are based in China, and the value inside of optical transceiver is distributed between 3 things. It's like DSP, photonics components, and assembly. Whereas once optical engine is developed, it means where you have a good coupling of lasers to silicon photonic modulators, then coupling of peak into fiber, and once LPOR is taken over, and you know, like there is a like pluggable using DSP, and then there is a very big push actually from Arista. They demonstrated that transceivers without DSP, but with much better design of PCB with good signal integrity, can be driven directly from ASIC, from good ASIC. And in this sense, the big value of overall transceiver world will come from laser, silicon photonics, and integration. And today, whatever people say, what we really see, only Intel has a true integration technology in the volume, you know, when they do wafer bonding of indium phosphide to silicon photonics. And there are tons of companies which are well-funded and which are developing, you know, this type of integration of laser to peak and fiber to peak. There are different technologies. I will skip it. You all know it, like edge coupling, vertical coupling, evanescent coupling. And there are pros and cons to be considered in different applications. There are, again, many activities to do flip chip on pedestal, or to couple light butt coupling, or microtransfer printing. Interesting technology of photonic wire bond from Vanguard. And also, let's say, if you talk about coupling of peak to fiber, there are a lot of developments of vertical coupling through grating and so on. And all of them, you'll have slides, right? All of them have pros and cons. And obviously, if one can really mount laser on silicon photonic chip and do butt coupling, then potentially it might be the best approach. However, the challenge for standard quantum well devices is so-called reflection back. If you have reflection back on a level of -25, -30 dB, traditional indium phosphide DFB laser will suffer from losing its coherency. You know, your DFB line start to get noisy and wider. There are a lot of work going on around coupling fiber into peak, different activities, different companies. At least what really catches the eye today, what Intel developed using glass, coupler and a holder, and then connecting it with the fiber in passive alignment. And by the way, you know, I have been hearing, you know, like about like V grooves for years now. People talking about coupling fiber through V grooves, but at least what we know that till now, you know, final active alignment is still needed. So somehow this issue is not resolved either. If you look into different technologies which will compete in order to win this race for 200 gig per lambda, or actually now, like a few biggest companies, they decided to develop SerDes which can support 448 gigabit per second PAM4 or 228 gigabaud. They started to develop the silicon. And now there is another challenge for photonics. We even cannot do today in the volume 200 gig per lane, but people are pushing, you know, to go to 400 gig per lane. So there are different technologies competing. It's obviously silicon photonic and thin film lithium niobate, which is like external modulation. And in this case, you need CW DFB laser to support it, or array of those, so individual lasers. And then indium phosphide is EML. EML, by the way, now they claim they can do even 400 gig per lane. But the problem, you have 8 lasers for DR8 transceiver, and you have to couple individually each one of them. And the question also temperature stability, because when you push the speed, you push one parameter, you start to sacrifice on others. So it's not yet clear whether EML can compete with silicon photonic and maintain their shares. So we hope, as we build CW DFB laser, and hopefully there are good solutions for integrated photonics, that silicon photonic plus CW DFB laser will win this competition. And actually market forecasts are going in that a bigger and bigger share will be taken by silicon photonic or thin film lithium niobate plus CW lasers. Here there is a prediction of, because SR8 is based on VCSEL, DR8 based on, let's say, silicon photonic and CW or EML. And even though it says like 500 meters, it's a standard, but majority of the link, especially to support AI clusters, it's like, you know, below 100 meters. And another one is FR4 or FR8, when you have CWDM laser split, it is by 20 nanometer or by 10 nanometer if you talk about 10 of them. So that's why I hope, again, that silicon photonic will win against the VCSELs. So a few words about Inalum. You know, Inalum is a company which is a spin-off from Yoffie Institute, and our professor, Jaroslav, he got Nobel Prize for semiconductor laser. Company was started in 2003 and really made some achievements in development of quantum dot technology. Actually, we were the first team who managed to bring quantum dots from research to commercial applications. And the reason, you know, people very often ask me now when we present our results and they say, okay, you have been talking about quantum dots now for decades. Why the progress is so slow? And the reason for that is that quantum dots are very slow by themselves because of damping of relaxation oscillation, and you cannot modulate them fast. That's why quantum dot technology had to wait until external modulation technology is well developed. And now we expect that after some peak of innovations, excitement like 20 years ago, and now productivity phase is coming. So Inalum, it's a company in Germany. We run our own manufacturing facilities. Recently, we started to invest significant amount of money in order to bring CapEx to higher volume. And we will be also working with contract manufacturers and most likely in Taiwan in order to bring lasers to high volume manufacturing. There is a markets, there are many of them where all-band lasers and SOA can support, and mainly, of course, it's cloud networking, AI clusters, and some others. Very interesting application of MCW LiDARs, where narrow line DFB is needed, which quantum dot can provide, and very high power booster optical amplifiers are also needed to substitute EDFA, which are used for 1.5 micron. And surprisingly, 1.3 micron turned out to be better eye safety and compared to 1.5 micron. So here's some record performance to demonstrate that indium arsenide, gallium arsenide quantum dots, DFB, can generate up to 125 degrees C, with a pretty good wall plug efficiency. Actually, nobody needs it, electronics doesn't work at this temperature. But 85, 105 degree, you can see pretty high power, unachievable in indium phosphide technology. So though, again, for pluggable transceivers, DR8, FR4, nobody needs power per channel more, let's say, than 150 milliwatt. And this is the product which we are ramping up right now. There was a nice demonstration at last OFC where two major transceiver companies showed performance, showed transceivers, LPO, it means linear drive without DSP, and quantum, instead of 4 DFB lasers for 8 channels, they used like 2 DFB quantum dot lasers for all 4 channels. And the main interesting things indeed, it's proven first time in the really production modes that we don't need optical isolator. Maybe it's not such a big deal, for active alignment for assembled transceivers, but once it comes to integration, it becomes very crucial parameter. So yeah, and I'll send you the link and very nice video recorded by Jose about this technology. So here's some measurement from our transceiver manufacturer partner, which demonstrates that quantum dot can sustain like -15 dB reflection back, and we expect it's about like 15 dB better compared to quantum well devices. There is interesting work going on also at Intel. They started, they do bonding of indium phosphide material to silicon photonic and build so-called hybrid lasers. But now they started to publish results claiming all those advantages of quantum dots. And there are recent publications on that if you bond gallium arsenide quantum dot wafer to your silicon platform, you might get certain advantage. Though, if I look into performance, so far it's worse compared to what they achieved with indium phosphide technology. So we also work, of course, on high power DFB lasers for ALS, actually for co-package optics, because co-package optics is envisioned in 2 flavors. One is like having fully integrated lasers, another one having external light source, where you have, let's say, array of DFB, and then you intermix all lambdas into different fibers in order to bring one fiber with multiple lambda to support peak, which sits next to ASIC, and then to distribute the signal. The estimation one would need about like 6 to 8 such external light source for one AI chip in the future. And then you can easily calculate how many lasers are needed based on prediction how many AI chips will be built in the world in the future. So if talk about arrays, we also have to say something here compared to indium phosphide technology. But I should say, the main advantage of this quantum dot technology, not just quantum dots, but gallium arsenide platform, because gallium arsenide is much more manufacturable compared to indium phosphide. If you think about silicon, silicon is here in terms of manufacturability. Indium phosphide here, gallium arsenide not far from indium phosphide compared to silicon, but still, you can do 6-inch wafers, you can, which is really much lower cost compared to indium phosphide technology. And the best solution, of course, to have co-package optics with single fiber bringing you several wavelengths instead of intermixing DFB array, because it gives you additional packaging challenges and losses in your AWG mixers. And this is the work we started to do many, many years ago. And now we feel it's like, like a second wind for comp laser, because quantum dots can also generate multiple wavelengths, being coherent, precisely spaced, because these are Fabry-Pérot modes. And then you have a single chip which can support multiple wavelength operation. Reliability. And this is a picture, if I guess none of us remember, but if you think about it, 70 years ago, those vacuum tube computers, they couldn't finish their simulation before some tuple failed. Now, if you look into AI clusters where people train the model, let's say, keep going for 2 days, and they cannot afford failure of a single link. And estimation that laser failure is a root cause for about 80+% of hardware failures. Main failure today, by the way, link flap, and it's not yet clear what is the reason. But if you talk about hardware, then it's lasers. Quantum dots, this is a picture from my PhD work in '99, before I went to Taiwan. In quantum dots, they have so-called like in situ window structure, because the typical reason for facet degradation, that you have overheating on the facet and your band gap shrinks and then start to absorb photons which are coming from the bulk material. However, quantum dots emit light at longer wavelengths, and means shorter, smaller energy, and that's why they're not absorbed on the facet, of course, if you cleave your laser between quantum dots. And they're much less sensitive to dislocations, So if you have quantum well, ideal quantum well, electron here, it's all the same. So all electrons will feel dislocations. But in quantum dots, of course, you have 3D localization, and that's why you are not that sensitive to it. Some reliability, some preliminary study from our customers, and pretty good results. We don't see basically any degradation. And these are our recent results. We're building now our machines for reliability. So here you can see even 105 degrees C. Statistics not big enough, but okay, we're building more. And these lasers, they have 135 degrees C PN junction temperature. We see some burning effect for 5%, and then it's stabilized. So far, we never observed like sudden failure of quantum dot laser. If you do something wrong, they will degrade. But we never observed, like in quantum well, you might have, sudden failure. And that's why people do burn-in in order to select infant mortality of the laser. So far, we don't see it. And if you can prove it in the volume, then once you guys build your integrated solutions, because the challenge is, okay, you want to put many lasers into your silicon photonic chip, but how do you burn it? You will burn the whole optical engine. It might be too expensive, But if your laser can have very, 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 very low infant mortality, then situation becomes much easier. So you bond them to silicon photonic, and then you burn in your overall peak with lasers without being scared that if one laser fails, the whole module will fail. And like few words about our recent development, which is really interesting. So we developed semiconductor optical amplifier based on quantum dots, which can support several modulated lambdas traveling through it in one regime. It's similar to EDFA, like people use EDFA in telecom to amplify many modulated lines simultaneously, which is not the case for quantum wells, because you will have too strong cross-gain modulation and lines will start talking to each other. On another side, if you run your quantum dot specially designed in high power, in high gain saturation mode, you can get very high power from a single stripe without tapered design with a very high efficiency, even at a high temperature. So that's why we say that with our quantum dots, we build kind of semiconductor analog of EDFA, which opens way to many other markets. And this is what I say about economics of gallium arsenide. You can use multiple wafer reactors. People sometimes are scared by MBE, but if you know how to run it, nothing to be scared, and there are big systems available. And to summarize, we would say that quantum dot lasers can make life of silicon photonics easier because of high temperature operation, especially if you want to put your, integrated engine inside of the box or close to your ASIC, then temperature is going to be high. We have to prove it in a volume, but we expect fundamentally better reliability. And obviously, gallium arsenide is better material for manufacturing. It's less fragile, it's cheaper. It's available on big wafers. Low alpha factor. This is a really cool advantage for integration, because otherwise, how do you integrate your laser and your silicon photonic? You don't want to put, some ferromagnetic like optical isolate in between, and then single chip WDM capability, where either this is like single SOA with WDM function, or comp laser, or high yield DFB arrays. Thank you very much for your attention.
Wow, really great talk, Alexei. Thank you very much for this, for the very clear introduction into the realm of integrated photonics, and also this comprehensive analysis of the market and the boom we're all facing in this market. It's of course also very encouraging to hear the story of Inalum, that your works originate already from your work together with the main Nobel Prize winner in the area, and the performance of the lasers is amazing. I'd say the proposition of Inalum is very clear, but here comes the question. So where us and the Taiwanese Optoelectronic Manufacturing Association can help you in your mission?
We need to ramp up high volume in gallium arsenide, number one, and we're constantly monitoring all integration technologies. Which one will win? There are like, I don't know, 20 companies now getting funded for that. And it varies from few million in Europe and from 400 million in the United States. the volume of finance being directed to this.
Mm-hmm. And when you say ramp up the volume, can you maybe suggest some numbers in your head for the future?
So it's again how you look at this and who will take the major market shares. We don't expect VCSEL to compete for 200 gig, but EML or silicon photonics integrated. So if silicon photonics takes 100%, let's make it simple to calculate the numbers, then I would say, like very soon, like 500 million DFB lasers will be needed on our side, 500 million DFB lasers.
Wow.
And of course, we have to compete with indium phosphide. Indium phosphide is doing tremendously good job. Like if you look into performance of CW of the indium phosphide DFB, like 4 years ago, now it's a big difference. And it's well-established companies, multi-billion-dollar companies, and we're a little, company in Germany with a big ambitions.
Okay. Wow. Yeah, that's fascinating. All right. So yeah, let me mention to all of you that so our EPIC online meetings are very interactive. So you're all very welcome to ask questions to our speakers. I mean, right now to Alexei, and also in the upcoming talks. So yeah, please just push the raise hand button at the bottom of the Zoom window, and then I can pass the word to you. And so you're welcome to ask the questions. Especially, I encourage our Taiwanese friends, since it's the first time for you at our meeting. So please, feel free to also turn on the video camera so we can see you and get to know you a little bit. All right, let me start with the question from Thomas Liu from BizLink, please. You can unmute. You need to unmute. Yes, go ahead.
Hey, hello.
Hello.
Hello, Thomas. Yeah, please say where you come from and your question.
I'm from BizLink. I'm located in Taiwan, Hsinchu. So I just heard about the speaker. He was also working at Hsinchu. Yeah, looks good.
In Kunming Village, on Confer Road, Kunming Village.
Yes. Yeah. And so far we have some project co-work with some Netherlands companies.
Okay.
And I'm very happy to join this webinar. And
Okay.
maybe we can talk more later on.
Okay, that's a good question. All right, so indeed, that's another story about the Epic meeting. So we're very happy to also bring you in touch with our speakers or actually anyone else in the room who might be of interest for you. So please feel free to also reach out to me or directly to the people in the room. You can also use the chat of this meeting to set up the contact by yourself. Oh, thank you, Thomas.
Okay.
Anyway,
Okay, thank you.
yeah. Yeah, Wilfred, would you have a question? Wilfred Noel from Foxlight.
Yes, thank you, Wilfred. Thank you, Ivan. Alex, very good talk. Great, nice new slides from light counting. I haven't seen those yet. Very good. Yes, it's getting quicker than what we thought. So, I mean, everybody's pushing for quantum dot lasers. You said it, Andreas, especially from Andy Bechtolzheimer is making a big. He thinks it's the next big thing, like next to lithium niobate. So you mentioned a little bit the heterogeneous integration that will take probably some time. Do you see but most people still use free space assembly? You showed the HG genuine and the Optolink. So how do they integrate the system then? Do you know? I think you mentioned there's no isolator. This makes things much easier. And
No, you know, like if you talk to those big transceivers manufacturers, they say no problem to do active alignment. We have 100 machines,
yes,
in a row.
that's what I'm getting at. Yes,
keep doing it. There is so massive capex investment, which is already amortized, and these companies now, like major transceiver manufacturers, grow this year. They will grow like 1.5 times in their revenue. So, and that's why today, I would say, it's not the major challenge for transceiver assembly houses to do active alignment and to integrate laser. You put laser, you put silicon photonic chip, you put one lens, you put optical isolate, you put another lens. Okay.
but
So
you don't need an isolator, from what I understood. That makes
no. Oh, this advantage. It's cost saving. It's also yield saving and it's less troubles and so on.
Yeah.
Yes.
Yeah.
But it's not. I would say it's not a kill app for active alignment. When it comes,
I'm not worried about active alignment. So because I will show that later, our optics are all actively aligned nowadays with the laser. But when we do designs now, we always have to take the big chunk of isolator into account, and this will be gone if they would use your laser. Is that correct? Yes.
no, that's correct. No, they all like it,
Yeah.
And there is a shortage envisioned now for CW, DFB, and also the funny thing, also for optical isolators, there is a shortage, because only 2 companies in the world build this Garnet,
Yes. I see. Thank you.
All right, and next question from Sylvie Menezo from Si-Photonics. Sylvie, please.
Yes, thank you, Ivan. Thank you, Alexei. I'm sorry I cannot put my camera. I'm sick today. I have a very bad cold, but I'm happy to have seen your very good talk, Alexei. I have a question. You mentioned you have it seems the industry is ready to make the quantum dot gallium arsenide on 8-inch wafers. How about the patterning of at this wafer scale? Is it ready? Is there
No, 6-inch, 8-inch, it's like 6-inch, yes. 6-inch it's a commercial standard now. Like there are here, FaceTime recognition based on gallium arsenide VCSELs, like pretty big arrays, and there are several billions of those arrays already produced in the world.
Do you see when do you foresee the 8-inch supply chain readiness?
It's not my headache for now,
Okay.
My headache how to ramp to 6-inch.
Okay, thanks.
All right, so that's all for you. So no more questions. In this case, I suggest we thank Alexei again, and looking forward again to set up your connection with Thomas, who spoke to us earlier, and also whoever else is interested in scaling up the amazing CW quantum dot lasers, please feel free to reach out to me or Alexei directly. With this, I'd like to pass the word to the first speaker from our counterpart organization, Tosia, and the first representative of Taiwan in our meeting will be Ted Kuo, the director of APAC Optoelectronics, and he will talk about the APAC's silicon photonic application solution. Ted?
Yes, can you see my screen?
Not yet. Please share the slides, and you'll be good to go.
Can you see it? Can you see it?
No.
No. Okay. Sure.
Okay. Now it seems to be starting.
Yeah. Okay. Today I will to introduce the AP Opto silicon photonics, our technology for the related application. So outline I will quick to give you the idea about our company, then talk more about our core technology. Then I trying to give an idea for the CPO, the fiber coupling solution. Then we're looking for the partner to do the development together. Then give you the summary today. Okay, so the AP Opto we founded from the year 1998, so more than 20 years. The optical transceiver shipping to the market, and we are the IPO company in Taiwan. So with the healthy the financial performance to support the long-term business, because the optical communication, the generation to generation investment is quite huge. And the third one is the quick talk about our product portfolio. We support a very comprehensive transceiver from the very low data rate to the 800, and right now we are developing 1.6 tera for all kinds of the application, no matter the data center, the switch, or the mobile front hall, even though the fiber to the home. Then today, because I will talk more about the silicon photonics related, then we have the technology platform to support this application. So this slide give you the introduction about our technology, from the design to the manufacturing as the package and all automation related. Of course, for the optical transceiver design, we need to have a capability from all kinds of the simulation, like the high-speed circuitry, optical system, the thermal and the stress simulation, and of course the validation platform. Then for the material wise, there's so many epoxy be used in the optical transceiver. So we have the know-how how to pick up the right epoxy, how to do the validation, and of course the optics related, no matter the active or the passive components, and high speed the substrate, and of course the oil composition. Then some software, firmware, and seamless compliant the development, and of course for the reliability validation platform. Then for the package wise, we have the internally the TOCAN and utility bonding the capability, and high precision the tree on board the package technology. Then for the automation, of course, like the die bond, wire bond, active aligner, the bending, and of course the testing. Then in the left side, I'll give the more idea about our the silicon photonics the technology platform, because we have experience to development the 800 DR8, the V group based silicon photonics the transceiver. Then for the 400 G the DR4, we pick up the edge coupled in the peak. So based on such kind of the transceiver, pluggable transceiver design experience, so our technology platform to support silicon photonics will include in, like again for the optical system design, then the precision, the die, all kinds of dice package, then the passive, the FAU attachment to the V group peak, and active or T transmitter side and the receiver side coupling, and of course the in-depth matching epoxy system. And of course for the CW laser, there's the higher power consumption with the heat. so the good thermal measurement capability for CW laser. And of course, we also can handle for the remote laser diode with the PM fiber measurement. Then we also have the remote, the CW laser, the optical module to support the CPO application. Okay, then this page, there's some high-level idea about our the CPO fiber coupling solution, because CPO is very hot in Taiwan right now. So we come out our idea and looking for some partnership. The feature, of course, for a CPO, the most people we talking with are looking for a detachable optical interconnection, and how to have such kind of the mechanical design. The most important is for the very low the coupling loss. Then we design the whole optical system. Then to support, based on if we using the match the more field diameter as the chart here, our do some simulation, then we can handle the window around the 20 micrometer to test the 2 dB the coupling loss to support for detachable the mechanical design. Then for the peak, we can support the vertical coupling, so you can see it's the pattern, something the structure like a TSMC is a vertical coupling, and in the right bottom side, we can also support edge coupling with the V groove, such kind of the peak. Then for the coupling process, our the system, our idea is to do the passive alignment, and for the tolerance, we need the bonding accuracy to below the 2 micrometer, so we can support the coupling, the better coupling loss, the better coupling efficiency, the lower coupling loss. And for the connector wise, because right now our idea is to come out something like the mini MT or MT like the mechanical structure. But of course, for if needing the more channels, we can discuss with our partner to come out the potential, the architecture. Yeah, so the purpose today, of course, is to looking for a partnership for the JDM. So our partner wishing to pick up the Si-Photonics, the design company, and also the package company. Okay, so I do the summary here. As our introduction, we have ready to go the Si-Photonics, the package and the testing capability, and we have the shipping record for the Si-Photonics, the pluggable, the transceiver. And the second thing is the major the target today to looking for the partnership from the PIC or the offset. Then the potential need to discussion the subject, for example, for the PIC. We need to discuss what FD from the waveguide design. And because our target is to do some passive alignment for our lens, then we need to discuss the bonding pad design on the PIC. Then for the offset as the high level, for example, the simulation, we're looking for the below the 2 micrometer, the post-shift accuracy bonding. I think it should be quite mature in the market, but anyway, if we have a partner, we can to discuss how to work together. Then for our portion, of course, we do the optical system design, the lens FAU solution design, and also the detachable, the mechanical, the solution design. Yeah, then if you have any question, you can ask me or you can contact. I showed my email in the slide. Yeah, it's my presentation today.
All right, this was Ted Kuo, the director of APAC Optoelectronics. Thank you very much, Ted, for a very clear presentation and also for summarizing your needs. I mean, for example, exactly. Thank you very much, Wilfred. I was already about to poke you about the optical design system. So please go ahead with your question.
So what you were showing in your request for CPO, I think we might have a solution for you. That's exactly what we're working on now, and I will show it in my presentation. So do you have more specifics on exactly what you need there?
Of course, I can waiting for your presentation, but basically we already contact you were the China team, and you were this
Okay.
guy. Yeah, right. Okay.
Thank you.
Yeah.
Thank you.
Okay, so the miracle has already happened. All right, and on the packaging and test side, I expect you wait for the Tech presentation as well. So Ying Chen will present their capabilities. I'm sure you will find some interesting overlaps there as well.
Yeah,
That's
sure.
right, Ying?
Yeah.
Okay, good. All right, any more questions from the room? Okay,
And I have a short questions. Just like you mentioned, this is a very interesting presentation from APEC. Actually, I guess I have visited APEC in China before, like more than 10 years before. And we were really interested to see the potential cooperation with APEC. And later I will present our solutions so that we can maybe have more discussion offline. And by the way, I'll be also in Taiwan in November. So maybe we can also, and also in mainland China. So maybe we can find a time to also organize a visit.
Yeah, sure. Welcome you to visit us.
Okay.
That's it. So Ted, we found all the solutions for you right here.
Yeah,
All right.
thank you.
Thanks again for your talk. And I suggest we pass to the next presentation, as already mentioned by Wilfred Noyle, the Chief Scientist of Focuslight. And Wilfred will talk about the micro-optics as enabling technology for datacom. Wilfred, whenever you're ready.
Thank you. So yeah, sorry. Thank you. Thank you, Ivan and EPIC for inviting me to this event. And I'm very happy to present what we do here. So you might know Focuslight already as a laser company, and recently Focuslight has extended our activities. So we actually have now 2 locations in Switzerland, one in Zurich and one in Neuchâtel still. Of course, we have several facilities and manufacturing sites in China with our headquarters in Xi'an, and in Dongguan is mostly the backend processing, and recently we also acquired Heptagon, which is also now in Singapore. So having said that, so we are having now these 4 pillars basically in our company. So the one is what we call photon generation. This is assembly and stacking and building of submodules for lasers. So we're making a lot of laser pre-packaged lasers that can as modules, as submodules that then become crucial parts in bigger systems. Then what we call photon control is everything that has to do with micro-optics and optics in general. So we we design our optics ourselves that can be then combined with the lasers, but we also sell that, of course, separately. So each of these columns is an individual business unit or business for us. Then we do complete solutions, mostly for the semiconductor industry. So we make alignment lasers for the how do you say, for the annealing in the display industry. And last but not least is our new column. It's the what we call the global photonics foundry, where we offer foundry services based on imprint technology and vacuum injection molding. So here we build complete micro optics. So for example, we make little stacked micro lenses, so all wafer level optics that are very interesting and competitive to classical injection plastic molding lenses. So this goes into eye tracking and systems like this. So this is a commercial foundry with super high volume for consumer applications. Also, what we do there is our automotive lighting. So we are also in automotive lighting, headlamps, and also in the so-called welcome or light carpet that you see sometimes for projectors. What do we do for this industry that we're targeting today or looking at today, so silicon photonics. So similar to the previous slides or previous presentations we saw, so we also offer a complete design work, and we're very happy to hear now that quantum dot lasers don't need an isolator anymore. That makes everything much easier. So we do microlens designs. So we design the microlens. So what is blue here, that's our part. What's gray, that we typically take from the client. And then we find the best possible solution. We also do tolerance simulation, and then we go into manufacturing. So we're also, like the previous two speakers, we are also wafer level. We do wafer level optics. And so we work on a wafer and make little polymer half spheres on there that are then by an etching technology transferred into the substrate. So in the end, you have a monolithic micro-optical element. Like here, this is a monolithic silicon lens. So, and then we dice to the size that the client needs. Yeah, we saw that already before in the keynote. I just want to mention, so this is the big thing now, the AI clusters, but there's a lot still going on in the classical data center technology and the telecom industry. As a matter of fact, so there was recently a presentation from Siena where they showed how they actually going into the edge now to 2 to 10 kilometers. That's very new. That means now you can even get coherent optics, coherent pluggable transceivers at the edge of the data center. They're not going inside the data centers, but this is being discussed as well. But they're already getting very close, which is a completely new thing, especially for 800 G LR and ZR. Okay. Similar as before in the keynote, the new players now in datacom. So if you would have looked at this configuration for data, telecom, and consumer a few years ago, it was completely different. So it's now very dominated by the Asian market and datacom, where telecom is still classically spread across the globe. Now Inolum, Coherent, and Source Photonics, Jabil, they're all Eoptolink, they all produce heavily in Asia. So this is where we are focusing, obviously, now our market on. And the volumes are mind-blowing, huh? We all heard that several times already. So what do we do in this domain again? So we do for fibers, we do the coupling lasers, the coupling lenses, and also for the lasers, we do the coupling optics for the collimation here. So we do either fused silica lenses that are then index matched to the typical glass fiber or single mode fiber, and the silicon lens is better for high numerical apertures, PICs or laser diodes. So when you have a mode field here of between 1 and 6 microns, which is typically, so lasers are typically with 1 and 3 microns, and PICs are typically between 3 and 8 microns. So we can have silicon lenses that can handle these high numerical divergence. Numerical aperture and divergence. So what we can do here is also making arrays, so that are then CTE matched to the PIC. So if you have a PIC with up to 16 channels, we see now 16 to 20 channels coming more and more often. For the 800 gig, 1.6 tera, we see 20 channels now coming, and that's where you need silicon microlens arrays that are CTE matched to the PIC. Yeah, I might just mention that we are going from free space now into silicon photonics. So we still have a lot of requests here for the 400, 200, and 400G. It's still going. So it's not because 800G and 1.6 tera is coming that the 400G and 200G are not there anymore. There's still a lot of demand for this. And we make typically these microlens arrays for the collimation. So these can either be singlets or arrays. But the trend is very important going now to make the multiplexers and the modulators in silicon photonics. It's also nicely explained in the keynote. So that means you need optics here to either couple the light to a detector, but typically what's more often the case, it's laser to PIC coupling or PIC to fiber coupling. So this is how our micro optics are used then. So you have some type of PIC with a lot of functionality here, and then we make different types of microlens designs and shapes and form factors that are then adapted to what the clients need. So we are again here on the laser diode side. We help the clients with the design. We get all the input information, and then we do the refocusing optics here for the laser diode. Sometimes these are very high NA systems. You have very large angles here of 60 degrees or so. And then on the other side of the PIC, typically there is a pluggable connector, so you want to have a collimation lens, so we do that as well. And then we also do the lenses that go in front of the single mode fiber. So we offer these 3 lenses, and we are able to do to help you here to find the best solution. So what the new development is when you have an edge emitter, so people kind of step away from the grading coupler now these days for different reasons. So there's a lot of silicon nitride now, spot size converters available, and also you want to go broadband. And for this, we offer this solution now with the microprism. So we have this little integrated lens with a prism and this vertical sidewall, then that you can basically attach to the end of your PIC, and then you use some off-the-shelf single mode fiber connector. So I can either collimate here or generate a certain beam diameter according to what you want. But what is more coming now, and we saw it also earlier today, is you have, when you make a PIC, you typically have some type of trench here already. And then what we're working on now, actually already with one foundry, we're working on the what we call the drop-in microprism. So you can push this micro prism inside this trench. So we co-designed that with a PIC manufacturer, and where we then can directly collimate the beam that comes out here. And what we see more and more often, nicely, that we saw this pattern already before. So we're also quoting this pattern from TSMC. What TSMC is offering now, this co-packaged optics for 200G per line, where you have a PIC and then you have some type of silicon carrier. The light goes through the back of the silicon carrier. There's some type of integrated lens there. And then what happens actually here, the light comes out as a very well-defined angle. And we see that now more and more often from all types of clients, where TSMC is basically defining the optical interface that comes above. So most of our optics that we design these days are to match what TSMC is doing here. So TSMC offers some type of output here, and we do an equivalent output for other silicon photonics systems, or we just design the optical collimator that's based on the TSMC design. So we are very flexible. So what we do there exactly is either we have these, you have some type of TIR mirror inside or grading coupler inside the PIC, and we do some matching optics here. So you have a collimated beam that comes out either vertical or at the angle, or we offer micro optics that you can attach to the backside to your silicon photonics device, and then we also do the fiber coupling here. So we are very flexible with what type of micro lenses we offer. So we have these backside cavities that are actually used as a beam expansion. So that means we have a mix between air and silicon here to get a certain collimated beam size here. So you can have a very thin silicon piece, or if space becomes rare these days in these transceivers, they want to get smaller and thinner, especially when you have to pack or stack two WDMs in there. So that means you have very little space. So by combining the expansion in air and silicon, we can make these nice trenches on the backside. So this is how it looks like then in reality. So you have some type of PIC or APD here. Then we do the silicon microlens that is then recessed, and people then put on microprisms, sometimes with the integrated, more or less assembled, pre-assembled isolator, and then couple into single mode fiber. So we see that quite often here, this type of configuration. And what is a little bit newer, what we're working now on, are these diffractive optical lenses that are, how do you say, they are fully off axis typically. They are fully flat. They are high fill factor, and they're fully integrated into this into the silicon slab. And then you can use it for an optical phase array. So this is typically for some type of free space optics, for let's say, for LiDAR applications or free space communication. So we see that now more and more often, and we're already working on this with different clients. So this is, so they come with their grading coupler output, and then we match our lenses. And the nice thing with this diffractive optical lenses, each lens can be different. So you can really generate some output field here, and each lens goes all the way to the edge. So there's no gaps between the lenses. So it's very versatile. So this is a summary again of what we can do. So we can offer these single lenses, these recessed lenses for the assembling with a prism, or we do all these different features here that help you to assemble and for your vision systems, and the prism lens. And also we offer a gold tin coating, very thin, actually less than 3 micrometer thin. So these are not electroplated. These are very thin layers that keep the alignment very well in the Z-axis. And that's all from my side. Thank you.
Thank you, Wilfred. Great summary as always. I'm sure we'll have some interesting questions about the micro lenses. Yeah, maybe we start already with Si-Photonics. Sylvie, please.
Yes, thank you very much, Wilfried. You mentioned you have multi-channel solutions. Can you comment on the performance?
So typically, these are our clients who do this. Sometimes they share the data, sometimes they don't. So typically, they go with what we've seen now is 20 channels. This is quite common now. So that we have done now several chip delivers for 20 channels. We don't usually get a feedback, but when the client orders again, then I think it's okay. So it's a very good question. I like to have the answer as well. Typically, it's so 1x4 is standard, 1x8 has been standard. We did 1x12 for many years already. So, and now the new channels are 1x20. So there we're still waiting for the feedback, but 1x8 and 1x12 we have been doing for several years already now.
Thank you.
All right, and now Cliff Wong from Wave Splitter Technologies, please.
I just want to ask if you think the grain coupling will become the mainstream, or edge coupling we grew with a many alignment system. But I think the grain coupling is the TSMC will want to promote a solution. So how do you think if the grain coupling will become the mainstream?
So that's a very good question. Excellent. I like to know the answer as well. So TSMC is very big, and of course, that's why I said TSMC effectively sets the standards now with their grading couplers. But we see more and more often broadband solutions, which are not based on grading couplers. So these are edge emitters. So most of the lenses we design now are for edge emitters. It's not clear yet. I think there will be both going. So the edge emitters and the grading couplers. So grading couplers have typical loss of 2 to 5 dB. Maybe Sylvie can comment on this. You might know better than me. But typically, the grading coupler has a certain loss, and with the edge emitter, we expect less loss, and everything is about low power now. Of course, the technology is a little bit more complex when you do edge emitters. So it's an excellent question. So we do a lot of optics for edge emitters. So we have been doing those for many years. So.
Okay. So maybe our end customer, they said that they don't like to take the fiber. So maybe that's why they want to use the grain coupling. Yeah.
Yes, so I think it's case by case. So also the V grooves have pros and cons. So we saw that Intel recently in their recent presentation, they said last year they showed a lot of V groove technologies. This year they said they're going away from the V grooves. So we have to see what's coming. Yeah.
All right, thank you, Cliff. Yung Chen from Rakentech, please.
So thanks to your presentation, Wilfried, very insightful, and especially about the micro optics, which is also one of our core business, actually components. I just wondering, because internally we also discuss a lot about the passive and active assembly, what will be the trend for the future? And do you have a more specific number about the tolerance which is allowed for the coupling between the so once the light go through the micro lens, which is collimated, and need to be aligned into the fiber array, right? And this step, what will be the tolerance so far you can achieve with your product?
So that's a very good question as well. So what we see now more and more that the mode fields that coming out of the PICs are between 3 and 6 microns. So sometimes they get a little bit bigger, but the spot size converter needs space, so people try to keep it as small as possible. So we see it between 3 and 6 microns now, the typical mode fields from the PIC. So then you can estimate the alignment accuracy needs to be half a micron or so or better. And on the other side, we see a strong trend towards a beam diameter between 40 and 60 microns. And more now, we see a lot of pitch of 127 microns pitch. So, and there's a beam diameter of about 40, 45 microns. This is becoming almost a standard now. We see that a lot now. So it's an excellent question. So I think the sweet spot for the 127 micrometer pitch will be around 40 to 50 microns, and for the 250 micron pitch, it will be between 50 and 80 microns, let's say. So the beam diameter outside, and then you can estimate your tolerance. So a very good question. So and for the we also have our recent project where we do the microprism. So there's the idea also to look into passive alignment, but this will be tricky. But this is something. When we say passive, that means you don't need light. You do everything with vision. So that's still like semi-active, let's say. So that puts also very high requirements on the accuracy on our lens design. So and we're working, and so we are very good at this. This is our core business, doing very precise front and backside features.
Yeah. I guess this is also something related to the mechanical design, not only the lens, the optical design, but also the mechanical, connection repeatability, right? Which will also be part of the tolerance. Yeah. Yes. I think this is an area maybe we have also a potential cooperation in the future. So we as a packaging company and you as optical companies, we can maybe work together to find a solution.
Yes, we have very close contacts to the team in Bremen. So we, and yes, let's
in Ahim actually.
Yeah. Good. Thank you. Yes.
Okay. Thank you.
But we have to go more in depth there. So that's right. Yes. Yeah.
Okay. Any particular also expectations from our collaboration with the Taiwanese optoelectronic manufacturers, Wilfred?
So yes, so for Taiwan, we saw it earlier. So we like to work closer with the PIC manufacturers there and also the assembly companies. And what we're actually looking into now is getting into PDKs or process development kits from the silicon photonics companies. So we're working very towards this. So we have already good contacts with the software companies, but at the same time, we're also looking into the ADKs, so the assembly design kits. And I think this is more dominant in Asia, Southeast Asia especially. And yes, and they would like to find partners, especially in Taiwan and other Asian countries, to get into the to make micro optics and micro lenses that are on site available at the assembly companies. This would be something very interesting for us. So yeah.
Okay. All right. So if that rings the bell to any of you, please contact Wilfred or me. And yeah, we thank you again for the talk, Wilfred. And I pass the word to our next speaker, Cliff Wong, the director of Wave Splitter Technologies. And he'll talk about the wave splitter laser chips and optical engine process flow. Yeah, Cliff, the floor is yours. You're good to go.
Can you see my slide?
Yes, all good. You can start.
Okay. First of all, I will introduce the wave splitter. So we established in 1996. So you can see our company name is Wave Splitter. So it's a passive component. So before that, we do the focus on WDM, PWDM, and the AWG product. But after 2003, we want to become an IPO company in Taiwan. So we established a RD team for the chip side and the transceiver side in Taiwan. So you can see the 2020 and the 2021, we established transceiver module and manufacturing in Taipei and established laser chip manufacturer in Taoyuan. And we also developed 10G and 25G. It's high speed DFB laser. And also in 2021 and 2022, we also developed a 3010 high power laser. It's the 70 milliwatt first at 70 degrees C. And in 2022 and 2024, we also developed 100 milliwatt for a CW laser. It's our global office, the headquarters in Taiwan. And as I mentioned, the transceiver side in Taipei and the laser chip side in Taoyuan. And we also have the sales office in Fremont. And we also had the Japan team. Japan is the sales office in Japan. And right now we have Vietnam. It's our manufacturer side. We also build up the Tosia, and the transceiver side in Vietnam. And China is our supply chain manager team in China. Okay. We had our core technology. We had three main applications. One is the CW laser, including the laser chip, and the laser chip array. It's the high power laser. And you can see the right side is 10G, 25G, 50G DWDM laser chip. It's high speed. So we will also focus on fiber to the hole, fiber to the room. And the left side is the sensor, optical sensing. So we also developed a 50-50 narrow line with DFB laser and the 60-53 gas sensor DFB laser. So we had the high power and the high speed and the sensor chip. It's our core technology. It's a very simple DFB laser chip process flow. So we buy the AP wafer from our supplier, and we also find the OEM to do the wafer process. After that, we in-house to do the scribe the wafer to the bar, and we do the face coating, and to do the AR, HR coating. And after that, we separate the from bar to chip. Then we do the TOK and the COC to do the reliability and the burn-in testing. So I want to show our chip current prediction. The high power laser, we also the 17 milliwatt is in mass production. We mentioned that 17 milliwatt is in 70 degrees C, okay? And the 100 milliwatt right now with the sample evaluation. So, and because we had the laser chip, so we also use our laser chip to develop our optical engine and the transceiver. So we also had a 400G DR4 optical engine. And by the next year, we will ready the 800G 2x DR4 LPO transceiver this year. And also we had a high-speed laser chip. So we had a 10G, 25G, 50G. So we use our chip to develop our home product. So like a BOSA or transceiver. And the 50-50 laser chip is we also developing right now. And I will show it's a very simple laser chip process flow. It's the wafer process. Okay, you can see the first drop is the AP wafer. Currently, we use the 2-inch or 3-inch to do so we buy the AP wafer, and then we had the first mask is to do the ridge. So we use the dry and the wet etching to do the ridge. Because our laser chip is a ridge waveguide. Okay, so we don't use the pH structure, so we use the ridge waveguide structure to develop our laser chip. So you can see the ridge. So we use the dry and the wet etching to do the ridge. And after ridge, we use the preservation film to protect. It's a silicon nitride. And after that, you can see we use the second mask. We open the contact. And after that, we start to do the P metal. It's a type PT gold to do the P metal, and then we do the annealing. And then after that, we do the gold plating. You can see the high power laser, the most important is the heat spreading. So we will increase the gold plating signals to help the heat spreading. So typically they use the 1 micron signals, but right now we use the 6 to 8 micron signals to help our heat spreading. And after that, we do the lapping, then to do the end metal. Okay, so it's a very, very simple wafer process. And it's our laser. You can see it's our 100 milliwatt CW laser. It's a typically IV curve. Okay, so it's the different shape is the different temperature. Okay, so it's a very, very, so it's just to show we can reach the 100 milliwatt CW laser at 70 degrees C. Okay, so as I mentioned before, our top core technology is our CW laser. So we use our DFB chip to develop our optical engine and also the LPO transceiver. Because we are not a tier one company, so we cannot get the DSP source. So it's not easy to get the DSP right now. So we only can develop LPO transceiver. Yeah. Okay. We had a 400 gig and 800 gig optical engine. You can see our left side is 400 gig optical engine. It's a 4-channel plan 100 gig. And you can see the left side is 800 gig optical engine. So you can see the two CW laser, but applied to the one peak 8-channel. So later on, I will show the optical engines the step by step. Optical engine. So we first step is we die bonding our CW laser into the surmount. So it's a eutectic bonding into the surmount. It's the first step. The second step, we die bond another component, such as we die bond the peak, we die bond the lens holder, we die bond the COC into the transmitter side base. And after that, we put the isolator and the thermistor and the MPD into the transmitter side base. And the second, we will put the TIA and the PD array into the receiver side. You can see it's the receiver side fiber array is active alignment. And after that, because when we finish the receiver side, we will start to do the transmitter side. And right now, we select the peak company that use the V-groove solution. So right now, we use the V-groove to do the V-groove. It's a passive alignment. So it's very easy to do the fiber attach and the high array for us. So we select the V group to use the V group pick company. Then when we finish the TS fiber array with the empty connector, so right now you can see after that the final step is we use the alignment to do the TS lens alignment. Yeah, it's the final process. And before that, we had finished the transmitter fiber array passive alignment. So you can through here to monitor the power level. So you can see when we do the TS side lens alignment, you don't know the power level. So but before that, we had to do the transmitter fiber array, so we can use this here to monitor the power level. Okay. So that's all from my side. Thank you.
All right. Thank you very much, Cliff. Interesting presentation. So if you have any questions for our speaker, please raise the hand. In the meantime, I wonder, Cliff, so at what scale can you produce this sub assemblies and everything you showed to us? And also, what is your expectation for bridging with the European Photonic Industry Consortium? Is there any particular need you would like to cover?
Yeah, I think the most important for us is I think the bottleneck will be the alignment machine. Yeah, so you can see we can do the lens alignment. It's very low throughput. I think when we use the maybe China company equipment or Japan company equipment, the throughput will be around 5 pieces per hour. So you can calculate if we want to reach the 100K per month output, maybe you need to buy 30 set alignment machine. It's only alignment machine. But you need to do the die bond, wire bond, and then this alignment. Maybe fiber array alignment. If you don't use the V crew, maybe you use the edge coupling, yeah, or grain coupling. So I think the most important, the bottleneck will be alignment machine. And as I know, if you press PO, press order to the alignment machine supplier, the lead time will at least 6 months, maybe longer. Yeah. So that's why we cannot compete with the China supplier because they had many equipment, such as maybe InnoLine, maybe Eoptolink. It's a Tier 1 company. They had more than 100 set equipment in their site. Yeah. So I think maybe I think you can see many activity will be used alignment. So I think for me it's very important to get this alignment equipment supplier support right now.
Okay, we got it. Well, we have a Phi contact right there with us. Ying Chen,
Yeah,
do you
I
have
know.
any quick comment on this?
Maybe you can see the lead time maybe will be longer.
Yeah, this is exactly what we see that a lot of customers are the challenge for a lot of customers of us, and this is also a reason why we this is the Phi contact preposition to provide the packaging technologies in high throughput and also yield, and also I will introduce this because I will be the next speaker. I will introduce more about our technology in my presentation, and offline we can also have more conversation. So like I said, I will be in Taiwan in November, and maybe we can also organize a offline meeting to present our technologies in a better way.
Okay, perfect. Yes, so Cliff, please pay attention to the next presentation. Yeah, very quickly, Wilfred, what's your question?
Thank you. So my question is, you showed a lot of pond. So there's a lot of hype for AI. all the transceivers that go into the AI business. Do you make lasers for both markets, or are you concentrating on the PON? And I would be interested in how these two markets compare in terms of costs, volume, reliability. So are there big differences, or?
Because it's a very big difference. Yeah, you can see the for the home application is maybe 10 key, 25 key, 50 key home application. It's a high volume. And for the AI data center, you can see currently we can see the many China suppliers such as Innolite or Yaptolink. Currently, they are still using the EML solution, so they don't use the silicon photonics because currently they can get the EML chip. Yeah, and yeah, I think, but they don't. I think maybe for the 800 gig or 1.6 tera, they will change. But currently, I heard they don't change because they still can get the EML chip from Japan's supplier. Yeah. So you can see such as their customer, NVIDIA or Google, they will consign the chip to Innolite or Yaptolink, so they don't worry about their chip supply. So they don't. So right now you can see they are still using the EML. So you can see how to convince them to use the silicon photonics. Maybe the cost, maybe if they can get EML chip. Because as you know, EML chip they need to regrowth two times. So the capacity is limited. But for high power laser, maybe we can increase the quantity very soon. So I think in the future, high power laser will be the future. Yeah.
Okay, thank you.
Okay, yeah, thank you, Cliff, once again for your presentation. And let me already switch to the next speaker. So Ying Chen, we already heard from him, presenting PyCon, and Ying Chen will talk about ecosystem for photonics packaging and testing. Floor is yours.
Okay, thank you, everyone. Let me share my screen. Can you see my screen already?
Yes, just remove the thing on the top. Yeah.
Okay,
And
it's now okay?
yes, better.
Okay.
Yeah, one more.
Okay, first of all,
yeah, good.
First of all, thanks to Epic and also Tosia to give us this opportunity to present our technologies. So my name is Ying Chen. I'm sales manager and product manager for Asian Pacific region and overseeing the indirect sales, such as in Singapore, Korea, Israel. I'm following up Silicon Photonics almost more than 10 years. So Si-Photonics is one of the German hidden champions. We are focusing on photonics packaging and testing solutions. We provide the solution worldwide. Since photonics now integrated into semiconductors, the challenge of semiconductor companies is the increased packaging accuracy requirement, and also need to maintain still the high throughput and also yield, and also the quickly evolving product development, as previous slides, the previous speaker mentioned already. But this is what exactly the solution from Si-Photonics can provide as an ecosystem. So we have different platforms which is suitable for the NPI phase, new product development, to the high volume manufacturing, which are proven by the top semiconductor companies. The comprehensive capabilities we have is such as high precision passive active alignment, and also we can do the testing and packaging on wafer level and also on die level. All platforms of Si-Photonics is using a unified API, which can ensure the seamless transition from MPI to high-volume manufacturing, can also minimize the disruption and also accelerate the time to market. Modular machine design is another advantage we have, which enhance the spare parts management, reduce the maintenance cost, and also at the end, lower the total cost of ownership. I think this is essential for all the suppliers, all the manufacturing companies. The high yield and throughput is another advantage, which maximize the overall equipment effectiveness and also ensure the operational efficiency. In the following minutes, I will demonstrate how we can achieve that. So let's dive into the total solution we provide from wafer to die. So we provide the optical electrical testing solution on wafer level. With this 3D printed periscope solution, we are able to do the edge coupling already on wafer level. For the double-side optical engine, we are developing the wafer level testing solution together with our customers and also partners, which are able to hot dock the ETA directly on the testing system and for the high-speed testing. So we also provide the packaging solutions for heterogeneous integration of 3.5 device onto silicon photonic chip on wafer level, but also on die level with very high accuracy. We are talking about 0.2 micrometer in 3 sigma. So for the die level testing, we also provide the high-speed OE testing solutions with parallel testing process, which can increase the throughput significantly. For the customer product, actually previous speaker has already talking about the transceiver modules quite a lot. So we have the different packaging solutions for the traditional pluggable transceivers, and also for the co-packaging technologies, and also including the external laser source. We have already delivered over 150 machines to the largest silicon photonic company to their CM in South Asia for the lens attachment and also FAU attachment of their transceiver modules. Almost 80% of the companies who is developing the CPO packaging technologies are cooperating with us. Therefore, our versatile platform can provide solutions such as fiber into V-groove attachment, lens array attachment, and also fiber array attachments directly on the CPO module. Besides this optical, already mentioned optical alignment and testing solutions, we ought utilize our understanding and experience in optics, and also together with our flexible platforms, we also provide the solution, the line solution for FAU assembly technologies, working with the largest semiconductor company in Taiwan. So due to time limitation, I won't be able to explain too much about that. Basically, we can start with a ribbon or single fiber and do the laser stripping cleaving, and then end up with the end-of-line testing, such as pitch size measurement, return loss measurement, insertion loss measurement, and so on. If you need any more information, please feel free to contact me offline. In terms of high accuracy heterogeneous integration, we provide also a special flip chip bonding technology with assistance of IR image system. We can achieve sub-micron alignment accuracy. So the principle of this technology is to use as the picture shows, I make a pointer. So we use the IR image system and also IR illumination. We can look through the PIC chip, and we can align the fiduciary on the top side of the PIC chip and bottom side of the 3.5 device die. And achieve sub-micron accuracy. And we use the advanced vision process, and together with the very accurate motion system, we can already achieve 0.2 micrometer in 3 sigma. And beside alignment with fiduciary, we can also use the waveguide as image to do the alignment. Okay, let me move to the next slide. Okay. In terms of high volume manufacturing, we provide the standalone machine with fully automatic loading system. We are also able to line up multiple machines with the conveyor system and provide the inline solution. So this is one example. We provide the whole line solution for the this is for automobile, and the whole assembly line has like more than 20 machines for the camera assembly. Our solution is SEMI S2 certificated and also can fulfill the cisgen requirement. Like I mentioned before, we have already delivered a couple hundreds of machines for customers, and now in this year we are delivering over 50 machines for one customer for their 1.6 terabyte transceiver modules. We build up our software architectures around our packaging and testing solutions. And we use machine learning technologies, nowadays more we can call it AI technologies, to process all data we can gather inside the machine and provide the following functions such as custom visualization for process parameters. We can put all of manufacturing data on one dashboard. Inline key parameter monitoring, which we call sometimes preventative maintenance. The machine will monitoring the data in production, and if there's any abnormal trend, then the machine will automatically send alarm to the operator or engineers. And we have also the capability to do the inline motion parameter optimization, active or passive alignment improvement. We use deep learning for inspection function. We have also visual system as a simulation tool. Customer can use it for the product development and also process development without touching the real machine, which is running in production. And we also have another very important function is so-called process control software. Imagine you have over 100 machines in the production line, and if you need to update the process, you can update all the process on one machine for one time without changing the parameters or process one by one, which is very time consuming and huge effort. So as a global company, we'll provide local service support from different FiConTech sites. We have very strong service team in the United States, Europe, and in China, and also in Thailand. And we are establishing a new service team in Malaysia and also one new subsidiary in Taiwan. With the application labs in Asia, in Europe, and also in the US, we also support customer product development and also proof of concept. This is a very short presentation about our company and solutions. Now we have a couple minutes for questions.
Okay, thank you, Yung Chen. Very nice presentation of FiConTech. Very briefly, my question is, what are your expectations for this collaboration with Taiwanese optoelectronic manufacturers?
Yeah, so we see the whole activities in Taiwan because now Taiwan is a very important market for us, and it's also one of my region I'm supporting. So since the biggest semiconductor company in Taiwan and also the whole OSAT and system integrators is working together for silicon photonics, and we need to work very closely together with them so that we can get the market trend in the first moment and also work together with the packaging and testing solution with them. And we believe that this will change the whole supply chain in the coming 5 to 10 years for photonics.
Mm-hmm. Yeah, that's a good summary of it. I hope. Well, you already got in conversation with several of our previous speakers, so I'm sure it's already becoming useful for you. So please feel free to poke in if any of this interests you as well. If there is no further questions, I suggest we move to the last speaker as we're already short on time. Thank you, Ying, again. And the last speaker is Justin Bracey, who represents Aerotech, and he will talk about how motion control enables modern datacom technologies. So for logistic reasons, Justin recorded his presentation, and later on his colleague Simon Chen we'll be able to take your questions. So it's coming now.
Hello, and thank you for attending this presentation. My name is Justin Bressi, and I'm a Business Development Manager with Aerotech, a global precision automation company that is headquartered in Pittsburgh, Pennsylvania. For those of you who don't know Aerotech, we've been in business for over 50 years, specializing in producing automation technologies that enable extremely high precision and high throughput applications in a variety of industries, including the optical communications industry. Our long heritage in this industry has positioned us well to assist our customers in solving the challenges of manufacturing and testing the devices that enable modern data centers. Should you have any follow-up questions related to this presentation, or if you are looking for general automation guidance, please reach out to me via email or LinkedIn, or feel free to ask questions at the conclusion of this webinar. Industry shaping trends like AI and high-performance computing have been evolving at a breakneck pace, continuing to push the limits of how we interact with the digital world. As these technologies grow more powerful and more ubiquitous in our daily lives, they're driving an insatiable demand for additional computational power at hyperscale data centers, demands that are currently outpacing Moore's Law. And while headlines tend to focus on this growth in compute demand, the bandwidth needs for communicating information from one system to another within data centers is following a similar trajectory. As established technologies have begun to see diminishing returns and in some cases begin to reach the limitations of fundamental physics, many people have claimed that the traditional understanding of Moore's Law is quote-unquote dead, or at the very least, meaningfully slowing down. Because of this, large-scale deployment of paradigm-shifting technologies such as silicon photonics and advanced packaging will be necessary to meet the demands of applications like AI and high-performance computing. In today's webinar, we'll delve deeper into these technologies and discuss some of the key process challenges in manufacturing and testing them. Speaking of silicon photonics, this technology offers several distinct advantages when compared to traditional semiconductor-based electronic devices. First, bandwidth and latency. Optical signals have been a foundational communication technology for decades, enabling data transmission at significantly higher speeds and at greater bandwidths than electronics alone. Additionally, optical signals are more resistant to external interference, reducing signal attenuation, particularly over long distances. High-speed optical interconnects within data centers take advantage of these properties. The next benefit is energy efficiency. Optical technologies that more tightly integrate photonic components shorten the lengths of conductive copper on the device, reducing power draw and heat generation. This is particularly critical as the power demands of data centers are growing exponentially. Finally, device footprint. Adoption of silicon photonics technologies has allowed transceiver manufacturers to pack more functionality into a smaller space, increasing the density of optical interconnects. Additionally, while still in the early stages commercially, emerging technologies like co-packaged optics offer the promise of replacing the industry standard pluggable transceivers with more integrated devices that are far smaller in both size and power demands. Because of these advantages, optical transceivers utilizing silicon photonics-based photonic integrated circuits already make up a substantial portion of the optical transceiver market, particularly for the highest speed devices, and this share is consistently growing. Another important and related trend of the fundamental technologies of modern transceivers is the shift towards tighter integration at the package device level. Traditionally, the optical engine of the transceiver, which includes photonic integrated circuits and a light source, is housed within the pluggable transceiver itself, as shown in the top diagram. However, enabled by advanced packaging techniques such as heterogeneous integration, where components of different materials are packaged together, new architectures, including onboard optics and co-packaged optics, are being developed to continue reducing both the physical size and power demands of these devices. By shortening the electrical paths on the device, signal robustness is improved and electrical resistance is reduced, lowering the picojoules consumed per bit of data transferred. Tighter integration is driving significant advancements in optical transceivers, but the downside of these increasingly complex architectures is that this complexity also introduces new challenges in manufacturing, testing, and packaging. Perhaps the most demanding aspect of both manufacturing and testing optical transceivers is the need for extreme precision, often on the micrometer and even nanometer scale. To meet these stringent requirements, manufacturers often must invest in advanced equipment and processes, including high precision positioning stages. So what specific processes require these micrometer and nanometer levels of precision? While not an exhaustive list, I plan to cover a few today, including wafer and die level testing of photonic integrated circuits, which is often performed to ensure quality picks before device packaging takes place. precision alignment for advanced packaging techniques, including heterogeneous integration and 2.5D and 3D chip stacking, and optical alignment and assembly, where components within a transceiver are aligned to ensure adequate signal strength. As you'll see on the subsequent slides, all these steps of the manufacturing utilize precision motion control systems in different and sometimes related ways. As I mentioned previously, silicon photonics wafers can be manufactured using traditional semiconductor methods, making silicon a very compelling option for photonic integrated circuits. Similar to traditional integrated circuits, both wafer and die-level testing methods are used for quality control, but testing PICs is a much different and more complex process than testing traditional electronic ICs. This is because testing photonic integrated circuits requires testing of both the electrical and optical paths on the die. For electrical paths, a simple physical connection is usually all that is needed to conduct a test. But for optical paths, devices are typically sensitive to the positioning of the probes rather than just contact. Because of this, precise probe manipulation is required, including in several degrees of freedom and in complex kinematic arrangements. As an example, shown here is a diagram representing edge coupling on a silicon photonic wafer. Precision, linear, and angular alignment between the probe and photonic device under test is required, as misalignments measured in micrometers and even nanometers can affect the signal loss during testing. Additionally, the adjustments made during these tests typically need to occur at the tip of the probe, so a system capable of pivoting about this point of interest is often needed. So how are these precision alignments executed? High precision positioning systems, such as the 6-axis direct drive Aerotech solution shown here, enable highly accurate placement of the optical probes to ensure consistent and repeatable device testing. Combined with Aerotech's Automation 1 motion control software and drive electronics, this system is able to pivot several degrees of freedom about the assigned work point and achieve off-axis error motions measured in single-digit micrometers, despite the work point being hundreds of millimeters from the probe's mounting point. Automation 1 simplifies configuration of these work point offsets, eliminating the need for the user to perform complex linear algebra. Additionally, alignment applications like this also typically take advantage of Automation 1's optical alignment algorithms to optimize the position of the probe based on an optical signal strength reading that is sent to the controller. The controller uses this signal strength to adjust the position of the system based on several built-in algorithms, identifying the ideal position for the probe to maximize the signal. Meeting stringent test requirements like these often require careful selection of an appropriate motion system, whether the system is a serial kinematic system like the one shown here, or a parallel kinematic system such as a hexapod. There are several advantages and disadvantages associated with both technologies, but one key advantage of serial kinematics is that the off-axis error motions introduced throughout the range of travel of each axis are much easier to characterize and therefore calibrate. This improves the repeatability performance of the system and reduces the risks of unexpected 3D error motions. To get a bit more specific, the 6-axis serial kinematic positioner shown here includes 3 degrees of freedom in each linear direction, as well as 3 degrees of freedom in each rotational direction, roll, pitch, and yaw. This system utilizes non-contact motors and high life cycle cross-roller bearings to ensure the industrial robustness and high stiffness, while also minimizing 3D geometric errors, capable of achieving 10 nanometer steps at the work point offset as shown in the plot, which was captured using a capacitive probe. This system's single-digit nanometer level in-position stability and minimum incremental motion are highly suitable for wafer probing applications. Next, I wanted to touch on advanced packaging, a key set of technologies that are enabling not only the next generation of semiconductor devices, but photonics-enabled devices as well. Advanced packaging encompasses a variety of manufacturing methods being developed and deployed primarily by the semiconductor industry, some of which, like TSMC's CoWoS, have been fully commercialized for years. Many others, like 3D stacking and hybrid bonding, are in various stages of development and commercialization, with expectations of broader utilization in the coming years. Advanced packaging methods like heterogeneous integration, which combine multiple chips of different materials into one package, are critical to the pursuit of more tightly integrated optical devices mentioned previously. This is because the material properties of silicon prevent it from lasing, so for an evolving technology like co-packaged optics to truly integrate the laser source into the packaged device, non-silicon materials will be needed to be incorporated. Regardless of the materials being integrated, as the feature sizes of these devices push into the low single-digit micrometer ranges, such as in the case of hybrid bonding, the alignment accuracies required during the integration process continue to tighten well into the nanometer levels. Various 2.5D and 3D stacking methods are being used for heterogeneous integration. While the specifics of each process vary and different manufacturers use different and often proprietary methods, These processes almost always require precision alignment at some point given the size of the components being integrated. For example, when aligning chips to an interposer for 2.5D stacking, individual chips are stacked onto an interposer, and the microbump contacts and through-silicon vias of the chip must align with the redistribution layer within the interposer to enable connections to other chips in the package. These types of alignments require precise linear positioning of each chip in the X and Y directions, followed by motion in the Z direction that is closely controlled for both position and force. For wafer-to-wafer processes, additional challenges are introduced as the angular positioning of the wafer becomes even more important than during a chip scale process. For example, for a 300 millimeter wafer, if the wafer is rotated about the vertical axis by even as much as 1/100th of a degree, this results in a linear misalignment at the edge of the wafer that's larger than 25 microns, and misalignments of this magnitude will result in significant defects and therefore reduce yield. As would be expected for any high-volume manufacturing operation, and especially so in the semiconductor industry, both high yield and high throughput are critical. So high-performance positioning systems that can combine the necessary precision with high dynamics are foundational to an optimized process flow. As mentioned previously, heterogeneous integration is required for co-packaging of optics onto a single substrate. Just recently, a major manufacturer of optical communications equipment debuted one of the first commercially available products that takes advantage of this technology, an optical switch that utilizes fan-out wafer-level packaging to co-package photonic integrated circuits with traditional ICs. However, scalability of these processes remains a key challenge for the industry, as many of the current approaches require aligning and stacking chips individually, which is highly time-consuming and therefore throughput limiting compared to most traditional semiconductor processes. Because of these limitations, new parallel processing methods are constantly being explored to reduce costs and increase output. One parallel processing method that is being explored at the lab level for heterogeneous integration is microtransfer printing. Microtransfer printing is a process that has been developed primarily for the production of another emerging technology, micro-LED displays. Microtransfer printing involves the transfer and attachment of an array of components simultaneously in a wafer-to-wafer format, typically. Since the wafer substrates can be different materials, microtransfer printing is a technology of interest for heterogeneous integration at scale. That being said, this wafer-to-wafer process is subject to the precision alignment challenges mentioned previously and therefore require highly precise positioning equipment like the example shown on the bottom right for execution. This system utilizes an Aerotech planar air-bearing XY stage and includes a total of 10 axes of motion for conducting planarity-sensitive alignments between the various components. The exceptional geometric performance and dynamic capabilities of the air-bearing stage enable in-spec alignments to be achieved at high speeds, satisfying the throughput requirements of this specific process. After the chip-scale packaging processes are completed, the final assembly of optical communication devices often requires high-precision alignments as well. Even though the feature sizes are often larger than at the chip packaging stage, precision positioning at several degrees of freedom is critical to reducing insertion losses, very similar to the positioning challenges discussed during the wafer and die level testing section. Misalignments during the final assembly can result in devices that do not meet quality and signal specifications. As an example, the plot on the bottom right shows optical signal strength during an alignment across a 20 micrometer by 20 micrometer range. And as you can see, the signal drops off considerably with just a few microns of misalignment. Fortunately, alignment algorithms like the one in Aerotech's Automation 1 controller are purpose-built to solve these challenges. Additionally, closed-loop position and force control is often necessary during these bonding processes, as parts can shift due to epoxy carrying temperature fluctuation and other factors. In the case of some types of optical devices, aligning multiple components simultaneously can also be necessary. Shown here is a solution from Aerotech that was for a specific optical device manufacturing application. In the case of this system, two separate optical components needed to be aligned at once, each with 6 degrees of freedom positioning flexibility. To accomplish this, Aerotech mounted two separate 6-DOF positioners in an inverted arrangement onto one of our linear motor-based gantry systems, all being synchronously controlled within a single instance of Automation 1. The linear motor technology enables the system to achieve high dynamics while moving between different devices, shortening the device-to-device travel time while maintaining micron-level positioning repeatability. Once in position, the 6-DOF positioners are able to align the components as needed using the Tool Center Point programming tool highlighted in the animation. Once aligned, high bandwidth closed-loop force control across multiple degrees of freedom ensures the appropriate forces are applied during the final assembly process. As you can see, automation solutions like this one require the deployment of complex, high-precision mechanics combined with advanced control features, which are among our favorite kinds of projects at Aerotech. To summarize, I hope it's now clear that precision automation plays a critical role in the manufacturing and testing of today's modern data infrastructure. Demand for bandwidth within data centers is increasing exponentially due to technologies like AI, a trend that shows no sign of slowing down. With traditional technologies starting to encroach on the boundaries of fundamental physics, innovations in paradigm-shifting technologies like silicon photonics and co-packaged optics will be needed to address these demands. Precision motion control already plays an important role in the manufacturing and testing of these technologies, a role that is set to become even more critical as optical devices become more integrated. Thank you for your time and attention today. Please feel free to contact me on LinkedIn or via email at jbressy.com if you'd like to arrange a follow-up discussion. My colleagues, William Ye and Simon Chen from our Aerotech Taiwan team, will now take some time to address questions from the audience.
Thank you.
All right. So this was the presentation from Aerotech, and I believe we have Simon with us to answer the questions. Hello, Simon. Yeah. So yeah, please. So this is the last talk of today's session. So very quickly, please raise your hands if you have a question for our speaker today. In the meantime, yeah, I'll ask. Yeah, Simon. So what is I mean, it's very clear the proposition of Aerotech, but what would you expect from this collaboration with the European Photonic Industry Consortium? What would be your needs that we as a European industry can cover?
Yeah, let me try to answer that. Simon is my colleague, and this is William joining here. Yeah, just I think this is the first time we actually joined this event together. And Aerotech, we are the company that is quite different from all other speakers today. So we are kind of the motion control automation company. So kind of upper strength compared to like Phycontech, they are kind of machine builder, like Focuslight and they all others they provide us kind of the final product, but we kind of like a component of an entire machine. So we would like to explore the possibility to finding the new trends of more difficult motion challenges that based on these new photonic devices. So because as all the speakers mentioned today about the alignment accuracy requirements and about the throughput requirements, it's very clear that we see, like, for example, the previous speaker, Cliff, he mentioned about the throughput is very a big bottleneck for him. So that's kind of the thing that we want to identify. Will that problem, the kind of bottleneck, is something related to motion that we can address? So, and not limiting to that, and just anything related to motion control, what can we do for kind of the photonic industry? Sort of like alignment, attachment testing processes. So these are all something we are very interested in.
All right. Okay, this is very clear. So I'm sure this might ring the bell for some of us in the audience. And if anyone, please raise the questions now. And if not, we're really hitting the time limit right now. So anyways, thank you very much for your presentation, Simon, and also your colleagues who actually recorded it. I believe we can be just in touch after the meeting for the follow-ups. And either way, so we thank also our partners from Tosia and all of the speakers who presented today for making this meeting possible. Let me just share very quickly some information with you. So this was the EPIC Online Technology meeting on Integrated Photonics Manufacturing with you, together with our partners from Taiwanese Optoelectronic Semiconductor Association. Yeah, once again, we heard very exciting talks from Alpha-Loom, APAC Optoelectronics, Focuslight, Wave Splitter Technologies, Phycontech, and Aerotech. And before you forget, let me introduce you the next occasion when we can meet and discuss the related topics of photonics integration and semiconductors. And this will be very soon, already in 11 and 12th of November in Munich during the famous Semicon Europe Expo that takes place in November 12 to 15. So we'll have the offline meeting of EPIC members and also all the associated partners there in Munich, right next to the expo, and then we'll go to visit the expo together. So yeah, don't miss the chance. There's only 2 weeks left, so please register now on our epic-photonics.com website. And this will be our next occasion to meet in person. So with this, I'm just there to remind you that EPIC Photonic Industry Consortium is there to support you with technology, expertise, market studies, networking, mentorship, recruiting, and investment opportunities. And I'd like to thank my whole team of EPIC that made this meeting possible, and all of you today for your attention. Thank you very much, and I'll see you on the next occasion.
Great.
All right. Thank you very much indeed.